Our next student design team is from Waterloo University. Waterloo Rocketry is a team of around 50 members, primarily undergraduate engineering, science, and mathematics students. Our presenters for today are Joel Goddard, current flight dynamics lead and senior airframe member at Waterloo Rocketry, third-year student at the University of Waterloo, excited about all things aerospace. We have Thomas Fairhead, current propulsion lead at Waterloo Rocketry. Thomas is passionate about liquid rocket engines and a big fan of the space industry in general. Today, Joel Goddard and Thomas Fairhead will present from Waterloo Rocketry and discuss their techniques and ideas for rocket apogee boost and much more. So please I'll give them the stage now.
Thank you. My name is Joel Goddard. As you said, I'm flight dynamics lead at Waterloo Rocketry, and I've also been doing a lot of airframe work as well.
Yeah, and I'm Thomas Fairhead. I'm the propulsion lead at Waterloo Rocketry right now. And we're going to talk to you about increasing the apogee of our rocket last year by 23% using iterative design techniques. So I'm guessing that most of you probably know who we are at Waterloo Rocketry, but in case you don't, we're about 100 people now on the design team based out of the University of Waterloo. We design, build, and launch rockets both at Spaceport America Cup and more recently at Launch Canada. The team launched our first rocket at Spaceport America in 2011, and most recently last year, we won second place at Spaceport America 2023 in 30K hybrid liquids, and we were also third place in basic launch category at Launch Canada 2023. Currently, we're developing a rocket called Borealis, which is a liquid rocket that is going to fly at Launch Canada in 2024. So yeah, just to give a bit of background about this presentation, in 2022, we had a rocket called Kraken of the Sky, which was going to compete in the 30,000 foot category at Spaceport America. That rocket was 6-inch diameter, it was 214 inches long, and it weighed 165 pounds. That was really not optimal. That rocket had a lot of issues. First of all, that rocket was not going to hit its apogee target. It was in a 30,000 foot category, and we would have maybe made it to 24,000 feet. Which is not really ideal when your points from the competition come from how close you are to the target. As well, that rocket was incredibly unstable, especially in high wind conditions. This was mostly because the rocket was really long, and it had 163 pounds of wet mass, and its thrust to weight ratio was not good. We also added a lot of mass to the rocket in the last 2 weeks before we left, which was not great for the fins. As well, this rocket had humongous slips in the timeline. It was really, really crunched.
Yeah, my favorite story about timeline slip is that year for competition, I got the opportunity to fly to competition and the rest of the team drove. So we flew to the competition and we got there and someone drove me to the hotel, and then when we got to the hotel, you know how they have that little 3 walls and a dumpster in the middle? There was 3 team members kind of huddled between the 3 walls to be sheltered from the wind with spray paint cans and the last few parts of the rocket that hadn't been painted yet, just quickly finishing up the painting of the rocket, which is definitely not what you want to be doing when you arrive at competition.
Yeah, and of course, because we were so last minute, there were a ton of integration problems on this rocket. The best part about this is that the CubeSat payload on the rocket literally did not fit. It didn't even fit in CAD. It wasn't like this was a mechanical problem. It just, nobody realized that it didn't go in, which was obviously not really optimal. And yeah, ultimately we didn't even launch this rocket. There was some issues with the competition, but there was also a lot of issues with the rocket that made us scrub launch attempts, and then it didn't even get to fly. So going into 2023, obviously we wanted to change this, so we started working on a new rocket called Leviathan of the Sky, and the goal was to iterate on COTS and actually make it to 30,000 feet. In addition to that, we also wanted to predict our apogee more accurately, because in 2022 we had a huge variation in the predicted apogee of our flight simulations. We also wanted to adhere more to our timelines, and we wanted to improve the integration so that it wasn't such a pain to put the rocket together.
Yeah. So the main thing here that we looked at in order to improve those issues and move into the LOTS design cycle was our design approach. So first I'm going to go through what our design approach was for COTS, and then we'll move into LOTS and look at the things that we changed to get there. So running through the design approach for COTS, first each subsystem kind of looked at their previous work, what they wanted to do, and they developed a conceptual design for what they wanted to do. This is done very independently, so Propulsion looked and said, oh, what kind of engine do we want to build? airframe looked and said, oh, what kind of composites do we want to make? And everyone kind of created a conceptual design independently for themselves. Then each subsystem moved into more detailed design once they had initial concepts. I'm sure a lot of engineering students are familiar with this approach. We also had bi-weekly integration meetings. These were to resolve issues that we found, but they weren't very frequent, they weren't super well attended, and because all the teams were very siloed, it was hard to find those issues in the meetings. It wasn't like that we were working super together, so it was very difficult to notice what issues we were going to have. Then, as a lot of teams are aware, right before competition we moved into very rushed integration and problem solving, things like making the CubeSat fit in the rocket, and lots of other things that happened very late in the design cycle that were very, very difficult to solve and very fast, and led to some of the problems at comp. Then lastly is competition, of course. And the main problem with this is that this approach really pushes all the problems that you discover right till the very end of the design cycle, and you end up with a rocket with a ton of problems that's not really finished when you're arriving at competition, which is definitely not what you want to do. So the issues with this is it's super linear, the subsystems all really struggle to communicate well, and no one on the team was looking at the whole system design of the rocket as a whole, which leaves you with a lot of integration issues and non-optimized parts. So moving into LUTs, we wanted to create more of a circular approach where we would do a bunch of steps every once in a while that would help us to come together as a team and consider the entire rocket as a whole. So I'll discuss one cycle, and then I'll talk about the different cycles we did. So first in each cycle is the same as before. We did a lot of design work. So this is either conceptual or detailed, depending on the project and stage. Then we would gather all of that design data from each subsystem and get it in one place. So that was mostly mass data, length data, engine data, anything else that we were thinking of. Then we moved into doing open rocket simulations. So taking all of that data and simulating the current status of the rocket and looking at where we were. Then for most of these cycles, we also did loads analysis to make sure that things weren't getting out of hand. And if there was any major changes recently, we could check to see how those changes affect the loads. And then as our team grew, specifically through this project, we grew from around 40 members on the team to closer to competition. We had around 80 people on the team. So as we grew, it became really clear that we needed really good communication to the rest of the team. And so what we did is started publishing a mini report at the end of each cycle. And we'll talk more about that later, but that really helped us get the communication out to the whole team and bring it to the wider group. So what cycles did we run? First, we did pre-cycle 1 or cycle 0, which happened right after the competition where we tried to launch COTS. And the main focus of this is what did we want to change from last year's rocket? What were the things we wanted to mainly focus on and iterate on? Then we moved into cycle 1. This is really focused on what is everyone's conceptual design and really deeply understanding that and looking for what needs to change. Mostly in things that we were sure were going to be problems or places where we could find optimizations which would dramatically improve our Apogee. Then we moved into cycle 2. This is like January, February timing. The main goal of this was to finalize the fin shape and design loads. And at this point, we also had our first static fire data, which was really helpful to make sure that we had confidence that this was like the rocket that we were going to fly. Then we moved into cycle 3, which was about generating accurate data for a competition report. So this was in March, April timing, which was right before the Spaceport America Cup final report. So this gave us really good confidence that what we were submitting to the competition was what we would actually be able to fly. Then we moved into cycle 4. This was focused on, as we built parts of the rocket, we would collect the data for each part individually with the actually built parts and simulate that to know what the rocket we were actually going to launch at competition was going to perform like. Moving into cycle 5, we started tracking mass based on assembly instead of based on part. This made sure that we could keep track of really small things. So when you paint components, they're going to get heavier. When you put all the bolts in, if you weren't accounting for bolts before, it's going to get heavier. If someone forgot to account for the batteries, for example, when you put the whole section together, you realize, oh, it's actually heavier than we thought. So this really made sure that we got really accurate data because we were measuring the whole assembly together instead of measuring everything individually where you can forget pieces or forget that paint adds mass. Then cycle 6 was really simulations at comp, which we can talk about later if there's more time as well, which is really critical for Spaceport 2022. And the big focus of this, again, is pushing the problems and opportunities that you discover early on to the design cycle. So especially in cycle 0, cycle 1, cycle 2, we were really focused on discovering problems and finding opportunities to boost our Apogee, which is very important for us. The advantage of this was obviously that we found those opportunities, and we usually kind of, as a benchmark, did cycles when we had new data. So for example, after a static fire, when we needed architecture decisions, so when we had to size the fins or we had to submit a competition report, and when deliverables needed data. So again, like competition reports or other internal deadlines that needed data. So moving into a little more detail about each of those 5 steps that make up a design cycle. The first one was gathering mass and length data. So we created this huge spreadsheet, which is pretty fun. And this spreadsheet contains minimum, expected, and maximum mass for each component of the entire rocket for every cycle. And so we have a whole bunch of these spreadsheets that we can look back on and analyze our designs. So this is a little bit more of a close-up. You can also see that for each source of data, we included the person who put in the data, the time they put in the data, and the source of the data. This helped us to make sure that the masses that people were entering actually came from good sources and weren't just made up ballpark numbers, and really helped us, especially later on, to know, okay, we remembered to weigh this part. We have this mass from the actual scale that we measured it on, and usually a link to a Slack message where you could verify that that was right. And then, if anything didn't match up, you could reach out to the person who entered the data and know when they put it in, so you know how recent the data was. We also included the expected CG of each component relative to the front of its section, which is very important for stability, and the length of each section, which our integration team worked a lot on. This let us generate some really fun graphs. So you can tell this graph here is showing where the mass in the rocket is distributed, both by subsystem and by section of the rocket. And one kind of really easy, really quick takeaway here is that propulsion mass is a huge part of the vehicle mass. So one of our big focuses really early on was reducing propulsion mass. And without generating this graph, you'd have no way of knowing that almost half of the rocket mass is for propulsion. So generating these graphs is really helpful. Another thing you can see here is that a lot of the mass is very far back in the rocket, which is actually not very optimal for stability. So another thing we did later was move mass forwards whenever possible, which helped us with our stability. Another comment I'll have here is that gathering all this mass data was very difficult. You have to get after people, and especially on a student team, it's very difficult to make sure that people respect the timelines you create and generate data that's actually accurate. So as a fun example of that, if people aren't complaining about your mass collection, you're probably doing something wrong. So here's an example of that. This is a pretty fun one here. My favorite part of this is my comments underneath that I actually want the weight of the whole assembly and the CG of everything as well, not just the weight of their section.
Yeah, so then after we've collected mass from everyone, we also had to do engine data tracking throughout this. So in order to do this, we basically used a custom spreadsheet and previous static fired data to generate a bunch of RSC files. And we generated new RSC files basically anytime we made a design change to the engine. And so we would update this with the latest data and design decisions every single cycle. And of course, before the first static fire, we didn't really have data from our engine for that year, but we used scaled thrust curves from the 2022 rocket in order to generate these things before we had static fire data. And then obviously you have to make the simulations once you have all the data. So we did almost all of our flight simulations last year in OpenRocket. We used OpenRocket because it's really reliable, especially when you're below supersonic, which is where we spent most of our flight. As well, OpenRocket has excellent documentation and is super easy to use, which allowed us to iterate really quickly through a bunch of different simulations. So yeah, we ran a lot of simulations last year. Every cycle we ran a bunch of simulations. So we ran an expected case. We also ran the minimum mass case and the maximum mass case. As well, we ran simulations in variable wind cases, and we used local weather data from past years to figure out what kind of winds we might expect. As well, we ran many simulations throughout the year that were just to check certain design changes. So like if you made a section 2 inches longer, how does that affect the rocket? We'd run a simulation for that. In each of these simulations, we tracked many different things. Obviously, we were looking at the apogee of the rocket with these simulations, but we were also looking at the off-the-rail velocity, which is important for stability. We also looked at stability numbers. We looked at minimum stability in both expected wind and in the maximum expected wind case. As well, we looked at maximum stability throughout the flight and stability at apogee. We also looked at maximum acceleration, which is useful for loads. And we tracked all of this stuff in a spreadsheet, which was super useful for traceability, and it was really useful late in the program and also for doing reflections after we were finished with competition. And yeah, we also did loads analysis in most of the cycles. We didn't do it in all of them, but we did it in most of them. And it's not really in the scope of this presentation, but basically we ran these loads analysis in a software spreadsheet thing called Bendit 7.
And then the last step here was the mini report. So in each cycle, we learned a ton of things and ran a bunch of simulations. So like we said before, with a large team, we needed to communicate that data to everyone to make sure that people could focus design energy on the things that had the highest impact to our system. So especially for big teams, this is important. As we grew really quickly, we needed to be able to communicate this to new members. And it was actually a really helpful resource when people joined the team to say, here's the rocket we're working on, here's a 10 to 15 page report that kind of gives the current status of the design and the things we're trying to improve. Also consider people's attention span. Especially as students, people aren't going to read your whole report. So one of the big things we did was we also created a 1 to 2 page version of this document that really gave the key details of each cycle and the things we were looking at. And specifically later on, we also, as we got closer to comp, we were running low on time and resources of people. So we started just writing that 1 to 2 page version because writing a whole 10 to 15 page report every time wasn't necessarily the best use of our time. There's also a table of contents on the slide so you can see kind of the main things that we were talking about in these reports. So now I'm going to give like a brief run through of all the specific design studies we did. There was actually a few more than this list, but this is a good summary. Another thing I'll mention here is that these are the things that we did for our rocket. I think this approach can apply for a lot of different projects, either student teams or not. And for rockets even, I wouldn't say that these are the specific design studies you should be running for your rocket. I think you should think about what your system requirements are and drive the design studies you do based off of that. Don't drive design studies based off of just some generic advice on what you should be looking at. First one we did was what diameter should we have. So COTS had a really long aspect ratio, and we wanted to see if creating a lower aspect ratio would be significantly better for lots. And it turned out it wasn't really. But we did investigate conceptual design of an 8-inch diameter and a 12-inch diameter rocket, which would be significantly shorter. But that was an interesting example of an unintuitive result. We thought it would be way better to do 8 or 12-inch, but it would be worse for our timeline. It turned out it would be worse for our timeline, and it would have been worse for the rocket. Another one we did was engine thrust optimization. So we were limited by regulations to be an O-class motor, so that means our impulse is constant, but we could change the maximum thrust and the length of the burn, basically trading those two. And through this, we were able to increase the thrust of the engine to 10.9 kilonewtons peak thrust, which gave us significantly better stability off rail and helped the system as a whole by about 1,000 feet, maybe even a little more if you consider some of the fin design changes. We also did a lot of fin shape optimization. Definitely did like over 100 simulations of fin shapes and lots of work on optimizing this. That gave us about 3,000 feet of apogee gain. We did a lot of work on mass distribution, like I mentioned before. Moving mass up the rocket is generally better for stability. There's some caveats to that, but mostly that's true. And then another thing we discovered kind of as we were going that we weren't expecting was that the surface finish of the rocket, which in hindsight is really obvious, has a huge impact on the apogee that you can reach. So we put a lot of work into both characterizing the surface finish that we had. So we used a surface profilometer on campus to be able to measure the surface finish that we had, and then also plug that into OpenRocket to be able to predict how that would affect our flight. And we also did a ton of work on various painting schemes, and people spent a lot of time making the surface finish really good, which gave us about 2,500 feet more of apogee, and also led to one of my favorite pictures of the flight campaign, where it's clear that you can see a reflection in most of our rocket, which is really fun. And that's now my Slack profile picture. Another kind of fun study was SRAD antenna length. So we were developing our own antenna to get live telemetry from the rocket, and they wanted to know if they could add empty space above the antenna to help the reception get better. So we did a quick simulation to see if 6 inches of extra length would hurt us, and it turned out it only reduced apogee by 50 feet. So we decided to give them the extra 6 inches, and we could decide that really quickly. It was like 1 or 2 weeks to a final decision. We also did a lot of length reduction. Overall, the rocket reduced by about like 10 or 12% of length. That didn't give us a lot of gains other than in structural mass reduction, but it also gave us about 300 feet from aerodynamic effects. Mass reduction was a huge focus of the program. The mass of the rocket was reduced by about 18% overall. A lot of that was propulsion improvements, but also a lot of that was just optimizing the parts, cutting holes in structural parts that didn't need to have like the whole mass filled up, adding slots, all kind of the standard engineering design decisions. That gave us about another 1,000 feet of apogee gain. We looked at doing a 70-75 aluminum ox tank. Horrible idea for a lot of reasons. We can talk about it later if someone wants to know. Another kind of fun study was looking at the apogee that we would get if we designed the fins for various wind speeds. So for example, if we only designed the fins for an 8-mile-per-hour wind, would we get significantly higher apogee? And we were able to kind of chart those two things, what wind speed we were designing for and apogee we would achieve. And this let us get confidence to design the fins to a high wind speed value, which turned out to be really important. Another kind of comment is that when we had manufacturing defects while we were manufacturing SRAD parts, we ended up switching to COTS parts for certain parts, including body tubes. And that was overall like a 1 pound mass increase in an interesting part of the rocket for mass. So we were able to run quick simulations to tell if that was going to be an issue, and decide in this case to prioritize our timeline and to prioritize our part quality and switch to COTS parts. If we didn't have these quick simulations, we might have been forced to struggle through the SRED design and really delay a lot of our manufacturing timelines and fight through integration issues. Another one is that we were able to tune our Apogee. So as we came up with all these improvements, we really went from 24,000 feet to, if we pushed it, probably 30,000 foot or 35,000 foot or 40,000 foot rocket. And so in order to meet our competition goals, we actually had to tune down the mass of fuel that we were loading. And so we were able to really bring that down to what we wanted and tune everything to create the system that we were trying to develop. Another one that has a long story to it is we were able to do live wind-based operations at launch. So basically we had an anemometer at the pad, and we were able to measure the wind speed while we were at our control center, which if you were at Spaceport last year, you would know is very important, as we mentioned we had historical weather data, and we designed the fins to 95th percentile winds. At Spaceport, there was 99th percentile winds every single day of the competition at around 12 o'clock. So, in order to launch anyway, we used an anemometer at the pad so that we could hold our operations if it was windy, similar to how SpaceX or another actual launch company would do it. And this actually was successful, as we were seeing like 25, 30 mile an hour winds about 5 minutes before we launched. So we decided to hold. We waited for 5 minutes. The winds went back down to 13 miles an hour, and we were able to launch successfully. Which, as far as I know, is the first time any student team has done that.
So yeah, what were the results of all of this sort of investigating? Well, we flew the rocket to 31,476 feet, which was a 3.7% error from predicted, which as far as we know is the smallest error of any 30K hybrid at Spaceport America ever, which is great. We also won second place in our category, and we won the best flight footage. The picture on the screen is from our flight. No, the Earth is not that curved at 30,000 feet. It is a fisheye lens, but it looks cool. And yeah, through this project, we also did found a flight dynamics sub-team. Yeah, that's right, we operated for 10 years on our team with no flight dynamics team, despite the fact that we flew a rocket every year. Now we do have a flight dynamics team. There's 5 members, and they work a lot on future projects. And we're using this approach again this year for our rocket. And yeah, there's a graph there that sort of shows our apogee prediction versus what our actual apogee was throughout all the cycles, from cycle 0 all the way up to cycle 6, which was the day of. And yeah, so carrying this forward to this year's rocket, I want to just emphasize that this approach isn't necessarily just applicable for one design goal. So with LOTS, the design goal was really to increase the apogee. But you don't necessarily need to use an approach like this if your goal is just to optimize for one specific thing. It's useful for any design goal. So a good example of this is this year we use this a lot to sort of define the requirements for our engine. Yeah, we basically, at the start of the year, we've never done a liquid engine before, so we had to sort of come up with a way to model this. So I basically made some idealized thrust curves, and we were able to test a bunch of different engine configurations using expected mass data from all the different subsystems, and we were really able to see, what sort of engine performance values we should be aiming for. The actual way that we did this, we weren't really optimizing for apogee at all, but we needed to still have a stable rocket. So we set our thrust value based on an off-the-rail speed that we wanted. And then we were able to set a burn time as well, because I wanted the engine to burn for at least 5 seconds. And so we used that to set a burn time value. And then that sort of led to mass targets for all of the subsystems. Like as early as September, we had sort of, here's how much your thing can weigh, and here's what the engine is going to be. And so that let us have a super early definition of what we wanted the project to be. And now we can track this as we move through the cycles throughout the year and make sure that everything is staying on track. Currently, for this design cycle, we're doing fin design right now. We're a little later than we were last year, but our competition's also later. And the new engine and a new air brakes project has added some complexity to this. That's the latest of it.
Yeah, I think that key about saying that your project goals really should determine what studies you're going to do and how you use this is really important. So some of the big lessons we learned here that you can apply either if you're on a rocketry team or in any engineering role is that cycle-based design is worth it, and system design should be considered from the beginning and throughout. So if every person is only looking at their individual system, when you put everything together, it's not going to work. So and you won't have an optimized system. So if you really consider the system design as a whole, from the beginning and then all the way throughout the project, specifically based on what your design goals are, you'll have a much better time designing. This is also a good point that changes early on are infinitely easier. So if you can push those problems and opportunities to the beginning, especially for propulsion stuff, you don't want to be doing a static part, then realizing you want your engine to be more powerful, so completely redesigning your engine and doing another static part. That's just not feasible. So it's important to set your design goals from the beginning and be able to set your requirements early so that you don't end up doing changes in the late stages. Again, setting requirements and goals carefully and communicating them should be a really high priority. That lets you make sure that you're not designing a system fully. That's not the system you want to be designing. Another kind of comment is that garbage inputs equal garbage outputs. So if you're gathering mass data and someone says, oh, my system's going to weigh 3 pounds, and you say, how did you get that number? And they say, oh, I just came up with it off the top of my head. Then your simulation is not even worth doing. Because if you give it garbage inputs, you're just going to get garbage outputs, and you're not really going to get a view of what's actually happening. Just a comment here, based on our experience in many student team rockets, especially experimental teams, there's a lot of performance left on the table due to this lack of system level design. One thing we want to specifically point out is thrust to weight ratio and off-rail velocity. For a lot of teams, especially like liquid teams or hybrid teams, we see people with really low thrust to weight ratios, really bad stability off the rail. And if you're careful in your early level design, you don't end up with that, and you can hugely increase your apogee. In our case, using the system level design, of course, it was like 23% improvement. Obviously depends on the project what you get. Another comment about simulations is that unexpected results should be expected. If it wasn't clear, supersonic rockets are unintuitive and very interdependent systems like other people have talked about. So those simulations and that analysis really helps you to be able to understand what's actually going on. You can work towards an intuitive understanding of what's happening, but it's going to take a lot of time and a lot of effort. Another kind of comment I'd like to mention is if you want extreme accuracy on the altitude that you're going to get, be okay with being a little bit extreme about that. So there's a lot of people on my team who would like to joke about gathering mass data and weighing things like lubricating fluids, little bolts, anything else that we're going to put on the rocket. It's all got to be tracked. And I think, in one sense, I don't think you have to do that in order to get very good apogee, but also that's what we did, and it led to very good apogee. So I don't know, you can learn that lesson there. Another kind of big point here is that documentation and knowledge transfer are really key. So kind of a really fun thing about Borealis that I haven't mentioned is that in our previous project in LOTS, there was a lot of people working on the team, and these results came from a ton of work from a lot of team members. It was mostly me, our integration lead at the time, who was a team lead, and our propulsion lead. And all 3 of us are almost not involved at all in the Borealis project. And yet we're using a lot of the same design approaches and a lot of the same lessons that we learned were transferred over to the new team that's developing the system. And if you're working on a student team, remember everyone on the team is going to be gone in 4 to 5 years. So you really need to focus on documentation and knowledge transfer. And that gives you a lot of fun things too, where you can look back at, oh, how did our mass change through the design cycle? Oh, did propulsion get lighter and other team subsystems got heavier, recovery? There's a bunch of cool things you can learn there that are really interesting. So yeah, if you're looking to contact the team, this is our email address. So if you have any questions about the presentation or our team in general, you can contact that. Another fun thing about this project is that I actually wrote a 40-page paper on this project and our design approaches. It has a lot more technical details, so if you want that paper, feel free to email me as well. We also have another paper on surface finish, so written by someone else. So if you want more technical details, feel free to reach out. And I also wanted to say thank you to all of the organizers of this conference and all the work they put in, and to you guys, of course, for listening to our presentation. So thank you. And then, yeah, we can do some Q&A as well if people have questions.
Sure. I'll speak loudly. Can you describe how you ended up at Waterloo Rocketry and what inspired you to get involved?
Yeah, for me, when I came to the university, I was very intentional about trying to get practical experience on the team or on our student team. So I went to go look at all the student teams that existed, and Waterloo Rocketry was the one that really was the most exciting to me. I think what other people have mentioned before, that rockets can inspire people, is a really helpful thing about teams and helps us in recruiting a lot. So for me, it was that desire to get specific engineering experience that was outside of the classroom and outside of theory, which has been incredibly useful for me, both in getting internships and like in general in career, to be learning hands-on instead of learning in the classroom. And then, I mean, rockets are exciting, so who doesn't want to work on rockets?
Yeah, for me, I also wanted to do student teams, but I specifically knew that I wanted to do rockets even in high school. I like during COVID especially, I was like obsessive in following all of the like SpaceX live streams and stuff. I was one of those kids, so I was really already into it. So when I came to the university, they had like the design team fair or whatever, and I just went to the rocketry table and talked to them for 2 hours straight. So I sort of already knew. But yeah, like again, sort of echoing what Joel said, like getting involved and doing it hands-on is so valuable and so worth it. And I have really enjoyed working on projects.
Thank you. I really enjoyed that talk. Can you hear me okay? Okay, I'll talk closer. I'd like to know what the distribution is in terms of workload across your team. You said you have 100 active members. In my experience, a small minority ends up doing the majority of the work. How do you handle that one person?
Yeah, definitely. So one thing is that it's around 100 people. I would say that, like you mentioned, probably like there's probably 50 or 60 people who are actively doing a large amount of work. And they are split into, we like to call them subsystems instead of sub-teams, which we think is a really helpful distinction because it helps people to work on multiple projects and be involved in multiple things. So that's one kind of comment, is that letting people kind of choose what they're most interested in and be able to kind of flow from one project to the next helps us a lot. Another thing there is, I think that with our co-op structure, I don't know if you know how Waterloo works, but we always have half of our students on co-op and half of our students in Waterloo. So that also makes it difficult because, okay, we have 100 people, but only 50 of those people likely are in Waterloo at any given time. So for example, like machining capabilities really changes based on what co-ops people get and who's free. So I don't know, there's a lot of approaches to that. I think having good subsystem leads who are really tracking like what's the project progress, where are the timelines, and who's working on what, to be able to like watch for things that are about to go wrong, and be able to like allocate those resources good. And also letting people kind of do things they're passionate about is really important. Because if you're not passionate about something, like you're not going to spend enough time to produce a quality of work that like our team's kind of grown to expect. So that's a big part of it too, is like the passionate people naturally will end up taking on more work, and that will kind of create the structure that needs to exist just based on the people's own passion. That really drives a lot of the distribution, I think. Yeah, I don't know. That's kind of a few answers to that question. But.
Yeah, and I just want to add one thing. Like, yeah, you're right that when you have like 60 people, it's really hard to like actually get anything done with 60 people. But when each I would say each subsystem, there's not really any subsystem that has more than like 5 really dedicated people on it, and then you have maybe a couple more than that for the biggest ones. But really, it is like still sort of kind of sticking to the small groups that do a lot of the work. You know, the first propulsion meeting of the year, we get 50 people in the room. We don't have 50 people working on propulsion stuff, and it's just, yeah, like the people who are the most passionate are the ones who are going to end up rising and doing the majority of the work. That's sort of how it always ends up. But yeah, I think we try to do a good job of giving opportunity to anybody who wants to work on something, try to find something that they'll be interested in.
In terms of collaboration, do you find it useful to collaborate with any of the local colleges that have skilled trades and bigger machine shops?
That's a good question. One of the things about our university is that they actually do a really good job of providing us with machining resources and other resources. So I think a lot of those needs for us are really met through our university. So for example, we have a machine shop that's pretty much dedicated to only student teams and some faculty projects, which is a huge blessing for us. And that enables us to teach our members a lot about machining as well. So I really think kind of the spirit of our team is to do as much as we possibly can ourselves. And so that's kind of led us to, for sure we work a lot with sponsors, but mostly try to do as much as we possibly can of the technical work or the machining work or any other type of fabrication work within our team as much as we possibly can.
You're lucky.
Yeah, we definitely are lucky in that side. especially like as the team has grown, it's been really cool to kind of get to see the resources that we can now access.
I went to find a pair of pants to wear today, and I realized like all of my nice khakis, every single one has like stains of oil from the shop. And I was like, wow, I guess this is me now. Just spend all day in the shop working on stuff. Thank you guys.